Yeah, welcome back after the short break. So, we do have here it is the third example. So, it is you can see that essentially we are adding one resistance at the emitter instead of having ideal bias current, and also we do have the RS at the base node. You can see the source resistance. Let you consider this RE 9.8 kilo ohms. So, let us change this one to 9.8 kilo ohms, and let us try to analyze the circuit to find the operating point of the transistor. So, to start with, let me draw the DC loop here. So, we do have VBB, which is 6 volt, and then we do have the RS, which is 100K, and then we do have the VBE on, this diode drop, and then we do have the resistance here RE. So, let you consider the current flow here, it is IB, and then of course, we do have the beta times of this IB current, it is coming from the collector. So, we can say that this is beta into IB. So, that is the IC part. So, the current flowing through this resistor on the other hand, it is 1 plus beta into IB. So, if I consider that this current it is approximately equals to beta into IB, and then if you analyze this circuit, namely if we consider the potential drop through this loop. So, what we can get it is in this loop, we do get 6 volt here, and then we do have 0.6 volt here. So, 6 volt equals to we do have IB into 100K plus 0.6 volt, and then roughly you can say that 100 times IB into RE, okay, and RE we said 9.8. So, what we are getting here it is IB multiplied by 100K. So, that is 10 to the power 5, and then RE we do have 9.8K. So, this is this plus so this is 9.8 into 10 to the power 5. So, this is equals to 5.4 volt. So, that is 5.4 volt is 6 minus 0.6. So, that gives us IB equals to 5.4 divided by 10.8, yes 10.8 into 10 to the power 5. So, that gives us 5 microampere. So, just make a note that we have intentionally have tuned it this resistance, so that we can get the same value of this I b what we have obtained in our previous example of 5 microampere. So, even if this resistance it is something else, of course, the circuit it will be working fine, but it is just for making this circuit comparable with the previous circuit, we are making this R e equals to 9.8. So, once you obtain this I b of say 5 microampere, so that gives us the I c equals to 100 into 5 microampere. So, the beta into this 5 microampere. So, that is equals to 0.5 milliampere, right. And then once we have the I c equals to this one, then you can calculate what will be the voltage here. Similar to the previous case, the voltage here it will be 6 volt here minus this drop across this R s, and this the drop it is 0.5. So, we can say the voltage here V b equals to 6 minus 0.5. So, that is 5.5. Let me use a different color. So, the voltage at the base it is 5.5. The voltage coming here it is 5.5 minus 0.6. So, the voltage here it is emitter voltage equals to 4.9 volt. So, that is 5.5 minus 0.6, and of course, the collector voltage here it is 10 volt. So, that gives us the operating point of the circuit. Now, using this these values of the quiescent currents and voltages, we can find the small signal parameter, and since the currents, particularly the collector current and base current, they are same. So, we can say that the GM value of the GM remains the same, namely 1 by 52 ampere per volt mho, and likewise R pi equals to 5.2 k, and then R naught equals to 100 k, right. So, we obtain the small signal parameter. Now, then we can find what will be the voltage gain, input impedance, output impedance, and so and so. So, let me use the same space and let me clear it, and again this we are considering it is 9.8. Sorry for the correction here again and again, but anyway we do have the voltage gain. You may recall the voltage gain A V. Since we do have the R e here, earlier in our analysis we have considered this resistance as R L. With that the voltage gain we obtain it is G m into R pi plus 1 into R naught in parallel with this R e, right. So, that is because we are having this R naught coming here, and this R e and R naught they are coming in parallel, because this terminal for signal it is AC ground. So, R naught and R e they are coming in parallel. In the denominator on the other hand, we do have G m into R pi plus 1 into R o in parallel with R e plus R pi. So, what are the changes we do have here? It is, this is of course beta plus 1. Now, R o it is 100 k, and R E it is 9.8 K, right. So, close to this one 9.8 K, or to be more precise it will be close to 9.5 or something like that, but whatever it is, say we approximate by this R E, say 9.8 K. So, likewise in the denominator we do have beta plus 1 into whatever 9.8 K, and then we do have the R pi. So, this R pi it is this is 5.2 K. Note that this voltage gain it is from this point to this point. We do have R S also to be considered, but attenuation of this circuit from this point to this point it is expected to be very small, even though R S it is 100 K, mainly because you do have the resistance here, input resistance here it is very high. But anyway, we will see that, but for the time being let you consider voltage gain from precisely at the base terminal to the emitter terminal. And even though this R E it is coming in parallel with R naught, because this we do have 1 plus beta getting multiplied. So, still this part it is dominating over this part. So, still and hence we can say that this is approximately 1. So, the voltage gain it is approximately 1. Now, let us look into the input resistance. So, let you consider the input resistance. So, the input resistance on the other hand it is as we have discussed before. So, this will be R pi plus G m into R pi plus 1 into R naught coming in parallel with R E. And again this is the input resistance looking into the base of this one, base of the transistor, without considering this R S. So, we do have R pi equals to 5.2 kilo ohms, and then we do have beta plus 1, and then this resistance it is whatever 100 multiplied by 9.8 divided by 109.8 into 10 to the power 3 kilo, right. And so, this part again either we can approximate by 9.8 or we can say that this is close to 9, but yeah, it will be very close to 9. This if you say that this is 10, yeah 11. So, that will be close to this one, but whatever it is we do have. So, if I approximate this part, or this is equal to very close to 9 kilo ohm. So, even then we do have 5.2 kilo ohm, and then we do have 101 getting multiplied with this 9. So, that is giving us 909 kilo ohm. So, that is equals to 914.2 kilo ohm. That is definitely it is higher than this resistance. So, the attenuation coming at this point, because the input resistance here it is given here, attenuation due to this finite value of R s which is I should say the voltage here with respect to this one, or rather base voltage VB with respect to V in, it is given by R in divided by R s plus R in, and R s is 100 K, R in it is close to 900 K. So, accordingly you can say that this is 914.2 divided by this is 1014.2. So, it is very close to 0.9. So, even if I consider this finite value of R s, then the voltage gain starting from the primary terminal to this point, even though I do have R s is quite high, still it is around 0.9, considering this R s. R s, high value of R s, right. So, that is about the voltage gain remaining close to 1. Output resistance we have discussed before. So, again we can go through that. Let me clear this, and yeah, this is 9.8 K as we have taken. So, the output impedance, it is, if I consider this part, this is giving us the output impedance very close to 1 by G m. So, R o, it is very close to 1 by G m, and then we also have this 1 by R e, and R e, since it is quite high compared to 1 by G m. So, this is remaining close to 1 by G m, which is 52 ohms. So, the upper cutoff frequency considering the CL and the output resistance, if I consider. So, this upper cutoff frequency coming from the output node, if I say that if U1, so that is equal to 1 by 2 pi R o into CL. So, this is remaining very close to 30 megahertz. And then if I consider the input capacitance, again C in, it is still well approximated by C mu, and hence if U 2, the second option for the upper cutoff frequency, which is 1 by 2 pi R s and C in. So, that part it is I should say I do have the R in also, but yeah, R in is much higher than R s. In fact, to be more precise, I should rather consider the R in also. So, we should consider R s in parallel with R in, and then C in. And of course, here this resistance, it is coming close to and this close to 100 kilohertz kilo ohm. So, again this frequency, it is very close to 1 by 3 megahertz. So, the conclusion here it is what you can say, that even if you consider R e and R s, still we do have the overall performance of the circuit, even with R s is very high, overall performance of the circuit or the qualitative performance of the circuit, namely the voltage gain approximately 1, and then input resistance is very high, output resistance is very small, input capacitance is low, and then the upper cutoff frequency it remaining high only, right. Now, if I consider the other resistance also RC, then of course, there will be a change. So, we will see that, but before that let you consider the MOS counterpart also, namely common drain amplifier. So, in the next slide we will be going for common drain amplifier. Yeah, so here we do have the common drain amplifier. Again, for this circuit also, to find the performance parameters, we need to follow the same procedure. Namely, we need to find the operating point, then we need to find the small signal performance parameters values, and then we can find the corresponding voltage gain, output resistance, then input capacitance, and so on and so on. So, here of course, the circuit it is different, slightly different. So, let us try to see with this example how do we find the operating point of the transistor. Remaining things it will be similar to the common collector circuit. So, let us try to see that. So, to get the DC operating point, let me consider this circuit. So, what we have here it is in DC condition Vg, if I say that Rs it is even though it is say 10k or 100k, since the current flow here it is 0 DC wise. So, the drop across this Rs is 0. So, we can say that Vgg it is directly coming to the gate node. So, if I say that Vgg equals to I do have the Vgs of the transistor, and then we do have the current flowing here, right. And this current flow of course, it is we do have say 1 milliampere of current. So, we are expecting that to find the voltage here, which is basically the Vgg minus this one, sorry, I should say that the Vs voltage or V out voltage, it is Vgg minus Vgs. Now, to find the Vgs, what you have to do, this is now IDS. So, we can say that IDS equals to I bias equals to the expression of the current, which is K W by L by 2 into Vgs minus Vth square, and we may drop this 1 plus lambda Vds factor. We can approximate this is maybe equals to 1. So, if I equate this part, what you can get here it is Vgs equals to Vth plus 2 times I bias and then divided by K W by L and then square root. So, here we do have Vth of the transistor, it is given here, which is 1 volt plus 2 times I bias, it is 1 milliampere, and then the device parameter it is given here, it is K W by L equals to 2 milliampere per volt. So, 2 milliampere per I should say this is volt square. So, what we have here, it is this 2 and this 2, it is getting cancelled, we have milliampere is also getting cancelled. So, this part as a result, it is we do have 1. So, the VGS, it is 1 plus 1 equals to 2 volt, right. So, that is the VGS. So, from that we can see that the voltage at the source, it is 6 minus 2, that is 4 volt. So, the voltage here, it is 4 volt, and of course, the drain voltage here, it is 10 volt, and gate voltage here, it is 6 volt. So, that gives us the operating point of the transistor. Of course, it ensures the transistor, it is in saturation region of operation, which is of course required, and then we can calculate the small signal parameter. So, let us try to see what will be the small signal parameter values. Let me use this space here. So, the GM, particularly the GM, it is K W by L into VGS minus VTH. So, what we have, it is 2 milliampere per volt square, and this is 1 volt. So, 2 into 1 milliampere per volt. On the other hand, the RDS, which is 1 divided by lambda into IDS. Now, lambda, it is given here, it is 0.01. So, that is 1 divided by 0.01, which is 10 power minus 2, and then IDS, it is 1 milliampere, which is 10 power minus 3. So, that gives us 10 power 5 ohms. So, that is the impedance we are getting for this RDS, and this is the GM part. So, using that we can find the voltage gain. So, you can probably for to calculate the voltage gain, let you try to remember the value of this VGS, the GM, and the corresponding value of the RDS. So, again let me use the space and clean it. So, what you are looking for, it is the voltage gain AV. So, what is the voltage gain of this circuit? The GM into RDS divided by GM into RDS plus 1, and GM, it is 2 milli, 2 into 10 to the power minus 3, and RDS, it is 10 to the power 5 ohms. So, likewise here also 2 into 10 to the power minus 5 into 10 to the power minus 3 and 10 to the power 5 plus 1. So, here in the numerator we do have 200, and in the denominator we do have 201. So, we can approximate this by 1. So, the voltage gain, it is 1, and then the output impedance. If you see the output impedance, R out equals to 1 divided by GM plus 1 by RDS. So, what we have here, it is 1 divided by GM it is 2 milli, 2 into 10 to the power minus 3, and then 1 by RDS. So, that is 10 to the power minus 5. All right. So, again this part it is dominating over this. So, we can approximate this by 10 to the power 3 by 2, which is 500 ohms. Of course, it is not as small as the previous case, namely as small as R out of common collector stage, but still it is low. And then if you consider, we do have the capacitance coming here of say 100 picofarad. So, from that we can calculate the upper cutoff frequency, but before that we can find what will be the C in. So, let me use different color for C in. So, now we are going to calculate C in, which is CGS. So, we do have the CGS part multiplied by 1 by GM RDS plus 1, you may recall this expression, plus CGD. So, this part of course, we do have here it is 201. So, we may drop this part, or rather I should say CGS we do have the 10 picofarad divided by 201, and CGD it is 2 picofarad. So, this part we can say it is close to, we can approximate this to by 2 picofarad only, because how much is it? This is 10 5 and it is just it is very small. We can ignore this part, definitely we can ignore. So, this is what the input capacitance. Now, if I say the upper cutoff frequency, let me again clear it and use the space here. So, upper cutoff frequency coming from CL, if U 1 equals to 1 by 2 pi, output resistance it is 500, and CL it is 10 to the power minus 10 hertz. So, we can multiply this 2 with 500 to get 1000 here. So, what we are getting it is 10 to the power 7 divided by pi. So, approximately equals to 10 divided by 3 megahertz, or we can say that this is close to 3 megahertz. Of course. And then the other candidate to define the upper cutoff frequency, which is coming from this RS and C in. So, if U 2 equals to 1 by 2 pi into RS, we are taking 100 K, 10 to the power 4, and then C in it is 2 picofarad. So, 2 into 10 to the power minus 12. So, this 4 and this minus 12, if you see, we do have minus 8 here. So, you can see it is 10 to the power 8 divided by 4 pi, or we can say this is 25 by pi megahertz, or we can further simplify if I consider this is 3. So, roughly it is 8 megahertz. So, that gives us the upper cutoff frequency. It is defined by this only. So, that is the upper cutoff frequency. So, that is how you can analyze this circuit. So, similarly, if I consider the common drain circuit with say resistance here R L instead of bias, then we can get the similar kind of performance. Probably you can work it out. So, let us see what is the circuit I do have for you. Yes. So, here we do have same common drain amplifier, but we do have R L having a value of 4 k, R S we do have same 10 k. So, instead of having ideal bias circuit, if we put say R L of say 4 k and then V G S of say 6 volt with whatever the parameter it is given here, then how do you find the operating point? So, this part since it is tricky, so let me explain to you. Rest of the things probably you can do it yourself. So, again if I consider this loop, what we can get here it is the drop across this R S is 0. So, we can say that gate voltage it is directly coming here DC wise, and then we do have the V G S here, and then we do have the IR drop. So, if I call this is V O output voltage, then VGG minus VO, it is essentially VGS of the transistor, right. So, we can say that the voltage here, on the other hand, if the current flow here it is say IDS, the voltage here it is R L multiplied by IDS. So, in other words, you can say that the VGG minus this VGS. So, that is equal to, so this voltage that is equal to IDS multiplied by R L. Now, this VGG, if you on the other hand, if I say that VGS and the so this is so I can say the other way also, say IDS equals to K W by 2 L multiplied by VGS minus VTH square. And then if I multiply this by R L, so what we are getting it is R L into IDS, but that is equal to this one. So, we can say that this is equal to VGG minus VGS, right. So, so probably we can try to see what will be its expression of this IDS from this, or how do we proceed. Maybe we can try to write this in terms of Vs and So, this is V s, and then so this is V s. So, from that we can say that V g s equals to no V s, sorry. So, V g s equals to V g g minus V s. Yes. So, now we can say that V s equals to this one. On the other hand, V g s you can replace by this V g g minus V s. So, we can, let me use different color. So, using this part and this part along with this one, what we can say that V s equals to K W by 2 L into R L multiplied by V g s, which is V g g minus V t h minus V s square. Now, let me put the value of different parameters here. So, we do have R L equals to 4 K, and this part it is 1 milliampere per volt. So, we can say that V s equals to 1 milliampere, 1 into 10 to the power minus 3, R L equals to 4 K, 4 into 10 to the power 3, and then we do have V g g minus V t h, that is 6 minus 1. So, that is 5 minus V s square, or we can probably, you can make it V s minus 5 square. So, V s minus 5 square into 4 equals to V s, right, or we can say that we can take this 4 here. So, we are getting V s square minus 10 V s plus 25, then minus V s by 4 equals to 0. Now, if you solve this second order equation, what we will be getting is that one solution you will be getting for V s is V s equals to, so the coefficient of V s here it is 41 by 4 with a minus sign. So, 41 by 4 plus or minus square root of 41 by 4 square minus 4 into whatever it is. So, we do have A into C. So, we do have 4 into 25. So, that is 100 divided by 2. So, if you take 4 outside, what will be having here, it is 41 divided plus minus. So, here we do have 41 square, and here you do have 16, yes. So, 4 square. So, basically you will be getting 8 81 square root divided by 4 into 2, 8. So, this gives you this is 9. So, we can see that Vs, I am using this space, sorry for clumsy here, clumsy arrangement, 41 plus minus 9 divided by 8. So, one solution, if I consider minus, one solution it is 4 volt, and the other solution, if I consider this is plus, that is 50 divided by 8. Now, this is not possible, that because the transistor enters into cutoff. So, we are not considering this one, we need to consider this one. So, if I consider Vs, the voltage here actually, so this is same as the source voltage Vs. If the Vs it is 4 volt, we have 6 volt. So, the voltage drop here it is 2 volt. So, that gives us Vgs is equal to 2 volt. If the Vgs is equal to 2 volt, then we can say that the corresponding IDs equals to K into W by L, that is 2 milli, and then divided by 2 into Vgs is 2 volt minus Vth square. So, that gives us 1 milliampere. So, again we are making this RL is equal to 4 K, so that the current flow IDs it is consistent with the previous example, right. So, let you consider that much of current, and it is consistent with the previous case. And once you obtain the value of this IDs, so then you can find the corresponding value of the small signal parameters. So, let me calculate the small signal parameter. So, I think we already have done that. Since IDS equals to 2 milliampere, no sorry 1 milliampere, the corresponding GM it was coming 2 milliampere per volt, and of course, the RDS it is same as the previous case 100 K, and rest of the parameters you can calculate yourself. So, I am not going to repeat that part. Now, if you have say RDS connected here, then what will happen? So, let me see that part. Yeah. So, we do have this RD also connected. We do have the RD connected here. So, what we said that we do have RD which is 4 K, and then RL also 4 K. Assuming this transistor it is in saturation, earlier we already have analyzed that for RL of 4 K, IDS equals to, so that is equal to 1 milliampere, and if this is RD is equal to 4 K, so the drop across this RD is 4 volt. So, we do have 6 volt coming here. So, this is 6 volt, and at the source we do have 4 volt. So, the voltage coming here after subtracting 4 volt from 10 volt, it is 6 volt. So, we do have 6 volt here, we do have 6 volt here. So, that this transistor it is still in saturation region of operation. So, that makes the circuit it is still working as a good amplifier, and then you can use the this IDS current and the VGS to calculate the GM, and this RDS, it still remains high, namely 100K. And so what will happen is that the impedances, particularly the output impedance, it will be having little modification. GM, the voltage gain, since the GM it is remaining same, voltage gain again approximately it will be 1. Output impedance, it will be having slight change. In fact, if you see the R out, if you look into this circuit, the R out it will be RD plus RDS divided by GM into RDS plus 1. So, that you can calculate. So, that is the resistance here, and the total resistance looking into the circuit, it will be this part coming in parallel with RL. Now, here if you see the numerical value, this part it may be dominating over 1, and then RDS it is also dominating. So, as a result, this part it is becoming 1 by GM only, all practical purposes, and then RL, even though RL it is coming in parallel, since 1 by GM it is 500 ohms. So, again this can be well approximated by 1 by GM, and it is 500 ohms. So, even though we do have RD it is there, but if you see the output impedance, it is remaining low, quote unquote low, and it is expected that upper cutoff frequency defined by output resistance and the CL, it is almost remaining the same. Only another important thing, you must be careful that voltage coming from this point to this point, it is also prominent. So, as a result, that not only the CGD it will be contributing through Miller effect, but CGS, but CGD it is also having Miller affected part. So, what is the voltage gain coming from the gate to drain, that we need to see. So, if you see the voltage gain coming from gate to source, that is approximately 1, that is what we said. But in addition to that, if you see the CGD and the voltage coming here, we call say Vd. So, V small d. So, that is definitely it is non-zero, and the voltage coming here it is V in multiplied by approximately multiplied by R d divided by so that is multiplied by G m R d divided by 1 plus G m into R L. So, if I consider this resistance is very high compared to R d, so that is what I will be getting, and this can be well approximated by R d by R L with of course a minus sign. So, now in this example, since we are taking both of them are equal, so we can see that the voltage gain from here to here it will be close to 1 with a minus sign. So, we can say that C in it is having primary contributor is CGD, but it is getting affected by this voltage gain 1 minus Vd divided by V in, and this part it is given here. So, from this equation if you see this part, it is CGD multiplied by 1 and then minus 1 is also there. So, it becomes plus 1 RD by RL. So, I should say that this becomes practically 4 picofarad. So, what is the conclusion here? It is, even though we do have RD here and we do have the signal coming here, since CGD it is small, then the input capacitance still it is remaining low, but we need to be careful that RD may be allowed to some extent, but if the RD it is coming more and more, then the contribution of the CGD to the input capacitance it will be large, and as a result the upper cutoff frequency defined by RS and the C in, that may be a problem. So, unnecessarily we should not be putting this RD. So, that is what the conclusion. So, let us see what is the design guidelines we can follow based on this knowledge. So, let me, I think I do have a slide for that. Yeah. So, here it is the analysis, the knowledge of the circuit analysis can be utilized, where in the analysis part we have started the calculation from top to bottom of this list, while these parameters it was given to us. So, that was the numerical analysis we have done for the common collector or common drain circuit. Now, if we have to make a design where in fact these parameters it will be given to us, voltage gain should be close to 1, then output impedance it will be given to us, then maybe for a given value of the load capacitance the cutoff frequency may be given to us. From that we need to calculate RO. So, this output impedance we can find. So, the way we will be proceeding while we have to design the circuit, it is basically from bottom to up, and so from the requirement of the output impedance, which we know that this output impedance is 1 by roughly 1 by GM, and that gives us the requirement here. So, then once we have the value of the GM, from that we can calculate what will be the corresponding IDS. So, what is the sequence? From RO we calculate GM, and then from that we calculate ID or from IDS, and to achieve this IDS we can find what is supposed to be the meaningful DC voltage and what will be the corresponding meaningful resistance at the source, and better we should avoid this resistance, and ideally we want this resistance should be 0. So, that unnecessarily we do not want to complicate the circuit, and contribution of the CGD we do not want to take it to the input capacitance, otherwise that will affect the upper cutoff frequency. So, the summary of the design guidelines is that we start from output resistance, particularly for common drain circuit, then we calculate GM, we calculate the required IDS. To achieve the required IDS, then we can find what will be the value of this one, and also the corresponding DC voltage here. In fact, this DC voltage it may be coming from the previous stage. So, in case if this is given to us accordingly, then we can calculate the corresponding RL. So, it boils down to the point that we need to calculate the corresponding RL of the circuit. So, similar kind of guidelines it can be followed for the common collector circuit also, where again the information may be given or rather requirement it will be given for the upper cutoff frequency for a given load capacitance. So, from that we need to calculate what is the RO, and this RO, since it is predominantly defined by GM, from that we can find what is the corresponding transconductance, and from that we can find what will be the corresponding collector current. And if the collector current is known to us, then for a given value of VBB, we can find what will be the corresponding RE. So, if VBB it is given to us, then the last thing it is we need to find the corresponding RE. But whatever the calculation we will be doing, we are assuming that the remaining parameters are given to us, namely the device parameters, particularly the early voltage and C pi C mu. Even though we do have so many parameters, but primarily we do have the main thing is the collector current and GM, it is defining the circuit performance of this voltage buffer. I think we need to conclude now. Yeah. So, what we have done today, it is we are we have concluded with numerical examples, and exhaustive numerical examples it is giving us to understand how we proceed for designing a circuit. So, the design guidelines of the common collector and common drain it is also covered, and so that is all about this second configuration. Now, in the next class we will be going for the other configuration, namely the common base and common gate configuration. Thank you for listening.